Hello again. Today we're going to talk about the time value of money and equipment economics. So as we know, the value of money changes with time. So how does that affect our estimate on the equipment economics, whether it's going to be better to buy the equipment today or buy it in a couple of years, or how we're going to pay for it? This is basically what we're going to be discussing in this lecture. So in the context of equipment management, a piece of equipment costs you $50,000 to purchase. You could also lease it or rent it. Which option should you choose? On one project you need to excavate 10,000 cubic yards of earth. How much does it cost you? Equipment A costs you $20,000 with a useful life of 5 years, while equipment B costs you $30,000 with a useful life of 7 years. Which one is a better value for your money? All of these are sample questions that any equipment manager or any project manager is going to be subject to, and will have to answer them based on an educated decision-making process. So what's the real cost of money? Money is a valuable commodity that changes value with time. An increase would be evaluation, or a decrease would be devaluation. And it's a super resource, which means it's used to buy any other resources or to acquire all the other resources. Because if you remember our definition of a resource, it's something that you need for the project, you have the ability to manage it, and that you pay money to acquire it. If it does not meet all of these three conditions, it is not considered a resource. The issues of costing and financing, which are two different issues, can make or break a construction operation or even a construction organization. So most of the construction companies that fail or declare bankruptcy, it's usually due to financing problems. They have not been able to provide the required amount of money at the proper period or point in time to meet their obligations for the project. So money has a time value which increases with time. Since money increases as we move forward from the present to the future, it also decreases in value if you move backward from the future to the present. The other concept is the concept of interest or usury. What's called interest is a fee assessed to use borrowed money. The percentage and amount of the fee will depend on the amount of money borrowed, the length of time it's borrowed, and the prevalent interest rate at the time of borrowing. So these are the three elements that control the amount of that percentage or that interest. Interest rate is the percentage rate charged against the borrowed capital or principal. So we need to know how is it calculated, and how is it going to affect our decision in buying or renting or leasing equipment. So what's the time value of money? We have to talk about something called the concept of equivalence. Payments that differ in magnitude but are made at different time periods may be equivalent to one another. In plain English, what does that mean? Any sum of money recorded as receipts or inflows, received money that we get, are called cash in. And any sum of money recorded as disbursements or outflows, money that we pay out, is called cash out. The difference between cash in and cash out at any point in time represents the cash flow at that point. So again, this is, as I said before, this is the major reason why most construction companies go bankrupt, because they did not cater for that difference between the cash out and the cash in. They might need a certain sum of money at a certain point in time. Failing to provide that sum is going to result in bankruptcy. So an example on cash flow, for example, if you buy a car today for $4,500, you have an outflow, cash out, of $4,500, which is represented by this negative $4,500. And then at the end of year one, you perform regular maintenance on that car to keep it in a good shape, good operating condition. So you spend on average $350 per year of ownership of that car. So the maintenance cost per year for year one was $350. For year two, the same thing. For year three, the same thing. And by the end of year four, you also pay that same amount to be able to sell the car. And then when you sell the car, you sell it for $2,000. So as you can see here, all of this, all the negatives are cash out, which are represented by a negative sign, and then you get a positive inflow or cash in of $2,000 when you sell the car. So this is an example of cash flow. The question now is, are these $350 equivalent? Are they the same? Since you spend one in year 1, one in year 2, year 3, and year 4, obviously it's not going to be the same, because $350 today is different from $350 a year from now, from 2 years from now, and so on. So in order to graphically represent the cash flow, because once you are able to draw the problem, to draw the cash flow, that's basically half of the solution. If you understand properly how that cash flow is dispersed, you can very easily solve the problem. The horizontal axis represents a timeline of the analysis, marked off in equal increments, whether they are months, years, weeks, whatever period, equal period. Receipts are represented by arrows directed upward, so the cash in is going to be moving upward. Disbursements or cash out or payments are represented by arrows directed downward, that's the negative. The arrow length is drawn to a scale proportional to the magnitude of the cash flow. So it's relatively these arrows are going to be relatively drawn to scale. Let's look at an example here. So here's the same example that we just discussed about the car that you purchased. You bought it for $4,500. You paid $4,500, so that's a cash out, $4,500. By the end of year 1, $350. End of year 2, $350. End of year 3, $350. End of year 4, $350. And then you sell the car for $2,000, which means a cash in. That's why it's pointing upward of $2,000. So once we do understand that, we can visualize graphically the cash flow of this problem. So now we're going to start talking about the different payments and the impact of time on these payments. Single payments may occur either today or at some time in the future. Like when you bought the car, you paid $4,500. That's a single payment. But it was made today, so it has a present value of $4,500. So P is used to indicate a sum paid or received today at the present. Whereas the $2,000 that you received 4 years from now, it's $2,000 future, because you're going to receive it in the future. So it's going to be represented by F, which is used to indicate a future sum. I is used to indicate the interest rate. So if you're going to borrow money and you're going to have to pay interest, what's the interest rate? The future value of a present sum invested at an interest rate I for a period of n years is represented as the future value of the money that you're paying today is equivalent to P, which is the present value, times 1 plus I to the power of n. 1 plus I to the power of n. I here is going to be represented as a percentage. So 5% is going to be 0.05. 10% is going to be 0.1, and so on. Therefore, if you're going to invest some money today, let's say $1,000 today, for 5 years, at an interest rate of 10%, we wish. So at interest rate of 10% for 5 years, we want to know what are these $5,000, what's this $1,000 that I'm going to pay today going to be worth in 5 years. So F, that's the future value that we don't know about, is equal to P, which is 1,000, times 1 plus I, 0.1, the 10%, to the power of n, which is 5 years, and that gives us the future value based on a known present value today and based on a known interest rate and known number of increments or number of years. The term 1 plus I to the power of n is called single payment compound amount factor, which is used to determine the future worth of a present sum of money. So to convert present to future, we use 1 plus I to the power of n. The present worth factor is actually the opposite of that. I have a future value. I know that I'm going to receive $5,000 in 5 years, and I want to know what's their current value today, what's their present value today. So the reciprocal, which is 1 over x, so it's 1 over 1 plus I to the power of n, of the single payment compound amount factor is called the single payment present worth factor. It's used to determine the present worth of a future sum of money. So to convert present to future, I use 1 plus I to the power of n. To convert from future to present, I divide by 1 plus I to the power of n. So let's look at an example here. A contractor plans to purchase a pickup truck in 5 years. He's going to purchase it in 5 years. So the purchase price we need to calculate is the one in 5 years, not today. So it's a future value. How much should he invest at a 6% interest rate today to have the $30,000 needed to purchase the truck at the end of 5 years? Let's start thinking about it. Let's start drawing it. What are we looking for? Are we looking for a present value, or are we looking for a future value? Which one do we know? What are the knowns in this problem? We have n equals 5, which is the 5 years. We have I, which is equal to 0.06, the 6%. And we have a future value, which is the value of that car in 5 years. That's $30,000. So I want to know how much money does that contractor have to invest today to get to $30,000 in 5 years. So the purchase price in this problem is a known future value F, 30,000, and the unknown is the present worth, which is P. In this case, P is equal to F over 1 plus I to the power of n. So 30,000 divided by 1 plus 0.06, which is 1.06 to the power of 5. That gives us that the contractor has to invest today $22,417. That's going to be equivalent to $30,000 in 5 years. Another example, a contractor bought a $15,000 pump with an expected service life of 10 years. So he bought it today for $15,000. That's a P. Its salvage value at the end of 10 years would be $4,000. Now, at the end of 10 years, which means it's a future value. What is the total cost to the contractor for owning the pump if the annual interest rate is 8%? Again, here we have a present value, we have a future value, and we have n, we have I. So we have all the ingredients we need to calculate the total cost at the end of these 10 years. So the purchase price is P, known. The salvage value is a future value F. We can either calculate all of this cost of ownership today, or we can calculate it in 10 years. So we can calculate it in terms of P, or we can calculate it in terms of F. Doesn't matter, provided that we know what is the point of time or point in time where we are making this calculation. So if we make this on the basis of P, it's going to be the $15,000, which is the purchase price today, minus the future value that you're going to receive 10 years from now, brought back to today's prices, which is a future value brought back to a present value. So we divide by 1 plus I to the power of n. I is 8%, n is 10, so we divide by 1.08 to the power of 10, which makes the $4,000 in 10 years equivalent to $1,852 today. Therefore, the total cost of ownership is going to be the $15,000 minus $1,852, which is $13,148 today. We could have solved the same problem in future to calculate what's the value at the end of the 10 years as well. Another example here, or another form of calculation, is going to be based on a uniform series of payments. So if you're paying for something in installments, let's say you bought a car and you pay, let's say, $500 every month for 4 years. The $500 for the first month is different from the $500 for the second month, is different from the $500 for the 48th month at the end of the 4 years. So it's sometimes necessary to determine the present worth P or the future value, future worth F, of a uniform series of payments. These annuities, or this regular amount that you're going to be paying every month or every year, is called an annuity. Uniform series of payments or receipts over a certain period of time. In other situations, it's necessary to determine the series of equal payments or receipts to equal a present value or a future value F. So it's either we're going to convert the P or the F into annuities, uniform series, or we're going to calculate what are these uniform series of payments equivalent to either today at the present value or in the future at the future value. So this uniform series compound amount factor is used to determine the future worth of a series of equal payments or receipts. It's represented as 1 plus I to the power of n minus 1 divided by I. That's the factor. The uniform series present worth factor is used to determine the present worth of a series of equal payments or receipts, represented as 1 plus I to the power of n minus 1 divided by I times 1 plus I to the power of n. Let's look at an example which is going to make these things much easier to understand. So the uniform series sinking fund factor is used to determine a series of equal payments or receipts that's equivalent to a required future sum. So if I say, for example, at the end of 4 years, I should have paid $20,000. How does that translate into annual payments? And uniform series capital recovery factor is used to determine a series of equal payments or receipts that's equivalent to a present worth sum. If I pay $20,000, if I have to pay $20,000 today, if the price of that car is $20,000 today, if I want to make that in 4 years on 4 installments, how is that? Are these equal installments gonna amount to? So let's look at the example here, which is gonna make things much clearer. A contractor is investing $5,000 per year in savings certificates at an interest rate of 6% and plans to continue the investment program for 6 years in order to be able to pay the down payment for new equipment. What will be the value of the investment at the end of 6 years? What do we have here? We have the contractor paying $5,000 per year, so this is an annuity. This is a repetitive amount. It's not just the present value today. It's going to be today, a year from now, 2 years from now, etc. What we want to calculate is F, a future value at the end of 6 years. So what we have is N is 6, and we have I is also in this case 6, which is a 6%. So based on A, which is the annuity, 5,000, I 6%, N 6, what we need to calculate is F, the future value at the end of these 6 years. Therefore, here's the equation. The annual investment is an annual uniform series, and the unknown is the future worth. Therefore, we will use the formula for uniform series compound amount factor. F is equal to A, which is the 5,000, times 1 plus I to the power of n minus 1 divided by I, which is 5,000 times 1.06 to the power of 6 minus 1 divided by 0.06, and that gives F, this uniform series of $5,000 over 6 years at the interest rate of 6% are going to be equivalent to $34,875. Another example, let's do the reverse. A contractor has purchased a new truck for $125,000 and plans to use it for 6 years. After 6 years of use, the expected salvage value will be $30,000. What is the annual cost or annual uniform series for the truck at an interest rate of 10%? So here we're going to use P, F, and A. P is $125,000. That's down, a down arrow of $125,000, which is cash out. N is 6 years. I, the interest rate, is 10%. And then we have a future value, which is the salvage value at the end of these 6 years of $30,000. So what are these equivalent to in annual increments, equal annual increments? So in this problem, the purchase price or the present value is known, as well as the salvage value or future value. The unknown is a series of equal annual payments. So we're going to convert the present value into annuities by using the equation, and we're going to convert the future value into annuities also by using the equation, But these are going to have two different signs, because this is negative and this is positive, or this is positive and this is negative, because they point into two different directions. So that amounted to 150,000 times 0.23, which is all of this stuff here, minus 30,000 times divided by 0.13, which is this amount here, which makes the annual payment to account for all of this transaction of $24,850. Okay, now we're going to look at alternative analysis. When two or more alternatives are capable of performing the same function, the economically superior alternative will be the one with the least present worth cost. So if I pay for this equipment in cash today, or if I pay for it in installments over 5 years or 6 years or whatever, let me make the comparison at the same point. Either convert both of them into annuities, or convert both of them to a present value, and that would be the better way, so that I compare present to present today. The option that's going to be more financially appealing and feasible is going to be the one that has the lower present value. So the present worth comparison, however, should be used only for assets with the same lifespan. I cannot now compare two pieces of equipment, one that's going to serve me for 5 years and another that's going to serve me for 7 years or 8 years. It has to have the same N number of years or lifespan. For assets with different lifespans, annual cost method of comparison should be used. So it's going to be based on annuities. How much is it going to cost per year? The annual cost method assumes that the asset will be replaced by an identical replacement at the end of the useful life. And this is basically the concept when we talked about the tax breaks and so on for the construction equipment and the depreciation. This is basically the concept. Why do we depreciate the equipment? Basically to have some savings that enable us at the end of the service life of the equipment to replace it. So the first step to compare alternatives is to construct the cash flow diagram for each. A common basis for comparison is selected, whether it's going to be present value, future value, or annuity. And an equivalent sum of uniform annual series is determined for each. Then the alternatives are compared to select the one that is most favorable. The contractors usually use the minimum attractive rate of return to perform cash flow analysis, which means if I had invested this money in another enterprise, it would have given me a return on investment. What would be the minimum acceptable return on investment or interest rate that I would accept to use that money for this, to buy this equipment? So for example, if I invested this money in the stock market and it would have given me a 6% return on investment, I should not buy equipment that's going to give me a return on investment of only 5%. It's going to be more profitable to invest in the stock market. But if buying that equipment is going to get me a return on investment of 7%, now it's more profitable than investing in the stock market, and that can make me make my decision. It's used as the effective interest rate in cash flow analysis. So again, examples make things much easier to understand. A contractor is considering the purchase of a used tractor for $180,000 that could be used for 10 years, N is 10 years, and then sold for an estimated salvage value of $10,000, so F is $10,000. Annual maintenance and repair costs are estimated at $15,000 per year, so this is an annuity, A. As an alternative, so this is the first part to be considered. The alternative is the contractor could lease a similar tractor for $4,000 a month. With the lease, he doesn't have to pay a high purchase price at the beginning. He's not going to have a salvage value at the end. And we know that the annuity that's going to be paid per month is fixed. Annual operating cost is the same for both alternatives. Fuels, filters, lubricants, etc. is going to be the same, so we're going to disregard it in both cases. The minimum attractive rate of return is 12%. Which option should the contractor select? So what we have to do here is to draw two different cash flows and compare these two, and then calculate the present worth or the annuity or the future value for both of them, and look at which one is going to be more appealing. So for the first option, we're going to pay $180,000 at the beginning. We're going to receive $10,000 at the end, salvage value. And then in the interim, for 10 years, we're going to be paying $15,000 per year in maintenance or whatever. Since the monthly rental rate is known, $4,000, we will compare the alternative on an annual cost basis. So the annual cost for the rental alternative, now remember that this is monthly, and the other one here, this is annual, so we have to bring it to the same increment. So we're going to assume for simplicity that $4,000 times 12, which is going to be the $48,000, this is what you have to pay as an annuity to be compared to this 15 and the 180 and the 10. So for the purchase alternative, the cash flow will look like that: 180,000, 15, 15, 15 until the 10th year, and then you receive 10,000 back. So for the purchase option, the annual cost can be determined using the formula. We have an interest rate of 12% for 10 years. So the purchase price, which is a P, times the formula to convert it to A, plus the A's, the 15,000 per year, minus the 10,000, which is the future value, converting it into annuities, which is going to amount to $46,290 per year. So this is the cost of ownership. Okay, we have just mentioned that the cost of lease or rental is going to be $48,000 per year. So we are comparing $48,000 for the lease option to $46,290 for the ownership option. Obviously, this is less expensive. Therefore, owning the equipment is going to be more economical than renting it or leasing it. Now, this is a summary of all the equations that we've discussed: the single payment compound, the single payment present worth, etc. So to convert from P to F, this is the formula that we use. So F is equal to P times 1 plus I to the power of n. To do the opposite, to convert an F to a P, so what we know is F and we want to get P, so P is equal to F times 1 plus I, 1 divided by 1 plus I to the power of n. To convert F to A, this is the equation. To convert P to A, to convert A to F, and to convert A to P. Now, I'm not going to ask you to memorize all of these equations. So on the test, I'm going to allow you to have a simple note card with these equations so that you don't have to memorize them. Contractors often want to estimate the prospective rate of return of an investment or compare anticipated rate of return for several alternative investments, just as we did. Is it better to buy the equipment? Is it better to lease the equipment? Is it better to invest in this project or another project or just the stock market? So we're going to look at different rates of return. The rate of return is an annual interest rate at which the sum of investment and expenditure equal the total income from the investment. It involves setting receivables equal to expenditures and solving for the interest rate. In many cases, the interest rate can be obtained from a trial and error method of solution. So 2 or more interest rates are assumed, equivalent present worth or annual costs are calculated, and the rate of return is found by interpolation. Let's look at an example, which again is going to make things much easier. So a contractor plans to invest $300,000 in used construction equipment. The estimated annual maintenance and repair cost, now the first one is a present value. Here we have annual maintenance and repair cost, annuity, $60,000. Expected annual income, also an annuity, $115,000. The expected profitable service life of the equipment is 8 years, so N is 8 years. What is the prospective rate of return on this investment? What is I? So what we're looking for here in this equation is I. Let's draw the cash flow again. So we have a present value that we're going to spend of $300,000, and then we're going to spend each year $60,000 in operating cost. In return, we're going to have a return on investment of $115,000 every year in return. So the problem can be solved based on the present worth, P, or the annual cost, A. The annual cost formula can be abbreviated as, now based on the table that we have looked at, A and P and I and N. So to get the A based on the P, 115,000 is already known, is equal to P is equal to another A, which is the 60,000 in the other direction, plus converting the P into annuities. So basically we're going to put this on the other side. So here we have 55,000 is equal to 300,000, and then the equation of converting a P into an A. The only unknown is the I, which is going to give us 0.183. Solution of this equation is going to give us 0.183. Through trial and error and using interest tables, we can start with 9%, which gives 0.181. Trying 10% gives 0.197. These tables, by the way, you can find them in any economics book, or you can find them online even. So the 9% gives 0.181, the 10% gives 0.197. What we're looking for is 0.183, which is closer to the 9%. So by interpolation, we're going to find that the rate of return is 9.3%, which is somewhere between the 9 and 10. That's basically our lecture on construction economics. We learned in this lecture about how to convert a present value into a future value, how to convert a future into present, how to convert either a present or a future into annuities, and how to have combinations if the problem includes present value, annuities, and future value at the same time, how to bring it into single terms, whether it's converting everything to future or present or annuities, and then calculating for the rate of return. I'll see you next time in another lecture.